Pennsylvania has 83,000 miles of streams and rivers, which puts it second only to Alaska in the United States. According to the Pennsylvania Department of Environmental Protection, the Water Quality Assessment Report found that 1/5 of the surveyed streams are impaired or polluted. This equates to about 1 of every 3 miles of streams and rivers in Pennsylvania. One of the leading causes of this water pollution is stormwater runoff, which puts sediments into the water through a process called sedimentation. Every stream has a natural amount of sediment in it. This is what normal amount of sediment in a stream would look like. As you can see, the water quality isn't impaired too much. This is the natural amount. But with human activity, that's what the streams start to look more like. This can obstruct sunlight from reaching the bottom of it, which can begin to kill the wildlife and can reduce biodiversity. Once the sediment reaches the waterways, the water can become cloudy, which obstructs sunlight and limits photosynthesis of aquatic plants, reduces biologically available oxygen, and increases water temperature. Sediment can clog fish gills, which reduces resistance to disease, lowers growth rates, and affects fish eggs and larvae development. This can begin to reduce populations such as the brook trout, which is the state fish of Pennsylvania.
Brook trout are like the canary in the coal mine.
That's because they thrive in only the coldest, cleanest water.
Their environment can also be degraded very slightly, and it can cause a large impact in the population.
Brook trout are suffering greatly from the overabundance of sedimentation. Brook trout have trouble surviving in polluted waterways, considering their natural habitat is cold, clean water that is void of heavy pollutants. Due to their specified habitual needs, brook trout are a key symbol of a clean habitat. Across Pennsylvania's ecosystems, brook trout are imperative to maintaining a healthy predator-prey relationship because they can prey on nearly any living organism of appropriate size. Changes to the ecosystem can affect brook trout specifically, and more concerning, the aquatic ecosystem as a whole. The reduction of sensitive species such as brook trout leads to a less diverse aquatic community. This reduction of aquatic species can be detrimental to other species in the community as well, because biodiversity is an essential component of all water systems. If a certain species or habitat is changed, it may cause a decline in one species, creating a chain effect. Sediment disrupts the natural food chain by destroying habitat or species, causing massive declines in fish populations. This current loss of biodiversity is becoming a large problem in function loss in these ecological systems.
Many sediment reduction solutions require changing the surrounding terrain or digging holes into the bottom of the stream, such as the use of sediment traps. While sediment traps have been widely used, they are costly to maintain and little information exists to evaluate their effectiveness in actually rehabilitating fish habitat. As with any filter, there is concern about trapping the very animals one is trying to save. Pulse is designed to address all of these problems.
Alright, so the first module in the Pulse system is probably the simplest. As you can see, it's basically a funnel designed to increase pressure so that water will flow quicker out of the final filter on the third module. What makes it unique is this galvanized steel mesh here, which slopes up to where there's a slot where the back end of the funnel connects with the second module, and that guides fish out of our system so they don't get caught and die, because obviously that's not what we want. We're trying to help wildlife. And it's sloped to prevent things from being sucked against it and blocking water flow.
So the second segment in our Pulse system is it's basically a valve that keeps the water at a constant pressure, and it kind of mixes all the sediment in with these series of baffles. And these series of baffles also mimic a valve designed by Nikola Tesla to keep the water in one direction. So if sediment heavy water in our cyclone were to come back, it would just go back in. And how that works is there's these series of baffles here, and then when it comes around, if the water were to try to go back through, it would come around and just get pushed back by the already flowing water. And this segment does not have to be this short. It can be much longer to account for, let's say you have a stream segment that's 30 feet long, but it only drops like 5 feet. So to get it level into our cyclone, you could have this, and then it would just be very long into the next segment.
The third segment seen here is the hydrocyclone portion of the pulse entirely. Basically the way it works is the water that's built up from the pressure from our last segment enters through here. This is just a support beam so that all the modular sections connect together. It'll go through here, and in here we have a roundabout tube that goes all the way around. And the way it's going to work is the water is going to go around, and the sediment is going to get trapped, and due to the centrifugal force, it's going to go around to the outside more. What's going to happen is it's going to create this funnel, and that funnel with that hydrocyclone is going to have the sediment coming towards the center at the bottom, where down below, you can look down here, you can see a pipe and an output section. That's where all the sediment's going to collect, and it's going to come out that pipe into another section, and that through that pipe it would go to a settling pond or some sort of settling area for the sediment to be further settled and taken away from the stream itself. And then the clean water, or the mostly clean water, would be built up in pressure and would rise up to the top. And out this area up here, which this also includes a sand filter, which takes out any of the smaller sediments, creating a more clean water, and this will just go right back into the system.
Alright, to elaborate on the final sand filter designed to take out the final sediment, you can't really see very well from here, but if you look from the top down, you see that extends well into the center of the hydrocyclone section. That's where all the cleanest water will be, so that it doesn't have to deal with being clogged by the larger sediment. And the benefit of making it a cylinder like that is that there's a larger surface area for water to hit and flow through, which allows water to flow through much quicker. The sand is only a couple inches deep, and that's because we're more concerned about having water flow at a reasonable rate than we are at getting all of the sediment out. And also we don't want to remove microbes and that sort of thing. It would be better to get, let's say, 85% of the sediment out and have a decent water flow than to get 95% of the sediment out and have a very slow water flow. It's just more efficient this way.
We can show the pulse here by using these blue dots to represent the water and these brown dots to represent the sediment in the water. Now, when it's entering the pulse through this funnel system at the beginning, it's still all clumped together in the water and hasn't yet to be separated in any way. But as it moves on to our next segment over here, which if you remember from our design, has a series of baffles that look something like this from the top-down view. And those baffles are going to create vortexes back and forth, where they'd create circular vortices in some of these areas upon collision. And that is going to cause the sediment in the water. So we have our water here. That's going to cause some of the sediment to displace. And it's basically suspending the sediment in preparation for the vortices. So over here you can see it's on this side, it's a lot more clumped together. But now in the second module, everything is spreading apart a lot more as a result of these vortices. Those smaller vortexes would still create separation otherwise, and then they move on to the third segment. In this third segment, the sediment is going to be separated out of the water by the force of the centrifugal vortex created in this huge third segment. And the third segment is just one big vortex, where it'll go around and around and around continuously based on the pressure. And that constant pressure is going to move that sediment to the outer edges of the vortex. And that's going to cause the cleaner water to come up the middle more. As the pressure increases, the stuff in the center is likely to go out the top, which this top part up here is the sand filter. And this pressure difference creates somewhat of a funnel. There might be a little sediment in there that's hard to remove. And that's why we have the sand filter up here, where the majority of this clean water, due to the pressure it's at, is going to exit out the top in the sand filter up here. And that's where those tinier spots, tinier sediment pieces here and here, all these little pieces, those are going to get filtered out by the sand filter, while the clean water will just go right back into the normal stream water. But what about the pipe down at the very bottom down here? Well, that pipe is going to collect more of this sediment over here, so all on the other side and opposite sides of the funnel, because the centrifugal force that's going around the vortex is going to keep it towards the outside, and it's eventually going to fall even with the centrifugal force due to gravity. And that's going to cause it to go out the middle at the bottom, and where it would in some way go down the tube all the way out into a separate settling pond where the sediment can further naturally settle and be displaced from the water.
The testing phase of the pulse took place in a stream smaller than the desired size for the implications of the prototype. For this reason, the pulse was unable to be completely submerged and tested to its fullest capability. Furthermore, the device was designed to be used in areas of high sedimentation, so its effectiveness towards solving this problem appeared less significant in this area of low sedimentation. The engineering behind the pulse held strong for the most part during the testing phase. However, due to a lack of resources, the accompanying sediment pond and pipe connection were unable to be implemented, showing how some of the concepts behind the sediment separation still appear to be theoretical. Multiple testing phases would have additionally benefited our device, allowing us to create a more effective sediment extractor, but this would have required more time and resources than what was available to us.
The pulse helps minimize the problem of sedimentation in rivers by filtering the water using a low-maintenance, low-impact, and efficient process. With enough widespread use, the pulse will help restore water quality in fish habitats and, in turn, protect the wider Pennsylvania ecosystem.
While researching and building the pulse, we were able to partner up with Carrie Calipson, the former lead agricultural teacher at Solanco High School, who has worked with the Pennsylvania Fish and Boat Commission on several stream remediation projects over the past decade. We were able to learn from him about the types of sedimentation seen in streams, consisting mainly of 3 levels in decreasing size: sand, silt, and clay. While our project wasn't centered around a specific type of sediment, this information could help with improvements and specifications to future models and prototypes of the pulse. Additionally, he further explained the concept of using a vortex to separate the sediment from the stream, and added that our vortex could be much larger in order to be more effective.
To improve the pulse, we have several ideas. The majority of improvements are regarding Module 3. There was one part that we could not make in the time allotted, and that would be a cylindrical grate that's concentric to the outer wall of the drum, set in a couple inches. The purpose of this would be to allow the extremely sediment-rich water that separates from the more clean water to, once it gets beyond that grate, slow down and be separate from the rest of the vortex so that the sediment could settle and be collected. We would also want to replace the aluminum drum with plastic if possible. And as far as the Tesla valve goes, for the second module, we could reduce the number of baffles to save material for other places. Other than that, as far as materials go, we really want to improve the connection between all of the modules, and we could use that using rubber rings and latches rather than the clamps we used as a temporary solution. We also want to phase out the screws and all metal fasteners because of concerns of corrosion and all that. So what we could do is manufacture tongue and groove style joints into all of the parts. These parts could then lock together on site and could be sealed using caulk. For scaling up, we would most likely make prefabricated parts which would then be assembled on site, except of course for the sand filter, which would have to be transported in one piece. As far as materials go, we would probably buy untextured PVC expanded foam in bulk rather than buying the siding, which would cost more. As far as making the drum out of plastic, we would need to use heated metal molds, which work pretty well for bending PVC parts. And we would also need to make custom cylinders for the sand filters rather than buying buckets. And that would have to be made using injection molding, which we would have to outsource because the equipment is overly expensive for our idea. The cost of making one of these mass-produced parts would be $340. $300 for the PVC, $10 for the stainless steel screen, $9 for caulk, $1 for sand, about $10 for assorted hardware, and for the sand filter casing, at least $10 for that. $340 sounds like a lot of money at first. However, keep in mind, this is cheaper than most high-volume sand filters, which cost about $460 a piece, and that's not even considering the cost for electricity to run them, which our pulse does not need. It runs entirely off of the power of the creek.